and take it away.
Yeah, I'll share my screen now. Sorry. Can you see my screen?
Yep, I can see it.
Okay, so I'll get started. So good morning, everyone. So today I'd like to introduce to you a method that we developed called MR-AHC. It is a robust Mendelian randomization method with two sample summary data based on the Agglomerative Hierarchical Clustering algorithm. So I'll start with introducing to you why we want to do cluster analysis in MR studies and how we can use cluster analysis to understand the causal mechanisms for multi-morbidity. And then I will show you how our method works and the features and advantages of our method. And then I will show you some of the results when we apply our method to estimate the causal effect of body fat percentage on type 2 diabetes, as well as the causal effects of body fat percentage on a pair of multi-morbid conditions, type 2 diabetes and osteoarthritis. So first of all, I want to explain to you why we want to do cluster analysis in MR studies. So in the Gemini project, which stands for Genetic Evaluation of Multi-Morbidity towards Individualization of Interventions, we have 3 work packages that conduct different but linked tasks. So first of all, the work package 1 would identify the multi-morbid condition pairs that are genetically correlated. And then in work package 2, we would carry on work from correlation study to causality study to investigate the shared causal pathway of the condition pairs that are identified from work package 1. And then after this, our results would go to work package 3 for clinical studies. So the work I'm presenting today is under work package 2, which is centered around the causal inference for multi-morbidity. And then the main methodology we are using is Mendelian randomization. So here is a brief recap of Mendelian randomization. It is a method that uses genetic variants as instrument variables to estimate the causal effects of an exposure on the outcome. So in MR studies, the main thing that we are interested in, the main thing we want to estimate is the causal effect alpha from X to Y. And also in MR studies, SNPs are commonly used genetic instruments. And from now on, we will just use SNPs to denote the genetic instruments. Okay, so in standard MR studies, it is usually assumed that, okay, the exposure affects the outcome in a homogeneous manner. This is to say, there is a single causal effect alpha from X to Y. Okay, so we can estimate the causal effect alpha using the summary data measured from GWAS studies, including the observed effects of the SNPs on exposure denoted by beta X, and the observed effects of the SNPs on the outcome denoted by beta Y. Okay, so under the assumption that there's a single effect from X to Y, then for all the SNPs summarized in G, approximately we would have this relationship. We have beta Y equals to alpha times beta X. So in this way, the causal effect alpha can be estimated as the ratio between beta Y and beta X. So we can also say that for each SNP in G, A has a ratio estimate, which is beta Y divided by beta X. And all their ratio under an assumption that there's a single causal effect, all those ratio estimates would be centered around the value of alpha. Okay, we can also make a plot of those SNP associations. So on the x-axis, we have the SNP exposure association beta X, and on the y-axis, we have the SNP outcome association beta Y, and each point represents a specific SNP, and all those SNPs are centered around a straight line with a slope equal to the causal effect alpha. Okay, but the problem with standard MR is that this single causal effect assumption, in some cases, it can be violated. Okay, so, sorry. I need to. Okay, so in some cases, this single causal effect assumption can be violated. For example, it might look like that we have a single exposure X, but it actually has different sum components. Let's call it X1 and X2. And more importantly, those sum components, they might affect the outcome Y in different ways. Like here, the X1, the causal effect of X1 on Y is alpha 1. But for the second component, X2, the causal effect of X2 on Y might be alpha 2, which is different from X1. Okay, so in this case, for all the SNPs in G1, which is correlated with the first component X1, okay, we have beta Y equals to alpha 1 times beta X. So in this way, for all the ratio estimates for SNPs in G1, it will be surrounded, it will be centered around the value alpha 1. But for SNPs in G2, which is correlated with the second component X2, then their ratio estimate would be centered around a different value from alpha 1, which is alpha 2. So we can say that if the single causal effect assumption is violated, we might observe multiple slopes in the data. Okay, so a well-known example of the violation of this single causal effect assumption is the heterogeneous causal effects of higher adiposity on type 2 diabetes. So when we try to estimate the causal effect of obesity on type 2 diabetes, we might use a single proxy for obesity, like BMI or body fat percentage. But the problem is that obesity, it is heterogeneous. So it has different subtypes that might have different metabolic effects. So for example, for some of the excess fat, like the fat stored at hips or thighs, it might be correlated, it might be associated with decreasing risk of those metabolic conditions. So we call it favorable adiposity. But on the other hand, for some of the excess fat, like the fat stored around organs, it might be associated with increasing risk of the metabolic conditions. So we call it unfavorable adiposity. So in the presence of favorable and unfavorable adiposity, when we try to model the causal effect of obesity on type 2 diabetes, it might not be a good idea that we use a standard model that only involves a single causal estimate. So instead, we want to account for different subtypes of adiposity and their distinct effects on the conditions. So in our paper, we use body fat percentage as a proxy for obesity and estimate the causal effect on type 2 diabetes. We use MR design with 487 SNPs, and this is the scatter plot of the SNP associations. So we can see that this single line might not be a good fit because it couldn't cover the points in the lower part. So instead, we might need multiple slopes to fit the data, which might reflect the multiple or heterogeneous causal mechanisms from obesity to type 2 diabetes due to different subtypes of adiposity. Okay, so to summarize, when there are different slopes in the data, which might reflect the multiple causal mechanisms from the exposure to the outcome, instead of using a standard MR model, which only estimates a single causal estimate, the thing we want to do is that we want to find out all the SNP clusters that drive distinct causal mechanisms, and then we estimate the heterogeneous causal effects. So this is why we want to do cluster analysis in MR studies. Okay, so next I will show you how we can use cluster analysis to help understand the mechanisms underlying multi-morbidity. Okay, so multi-morbidity, it is the coexistence of more than one long-term conditions in an individual. And in our Gemini project, we mainly focus on the multi-morbidity condition pairs that are genetically correlated. So for these conditions, they have shared genetic components underlying their coexistence. And our work package 1 has discovered that for some of these condition pairs, their genetic correlation can be largely explained by a common risk factor, obesity. So for example, still the findings from our work package 1. So we have two conditions, or parallel conditions, type 2 diabetes and osteoarthritis. And okay, we found out that, okay, they are genetically correlated. And their genetic correlation is around 0.3, which is illustrated by this blue line. But after we control for BMI as a common risk factor, we found out that their genetic correlation reduces to 0. So this means that we can say that the genetic correlation between type 2 diabetes and osteoarthritis, it can be entirely attributed to the BMI genetics. So this result motivates the multi-morbidity model that we are interested in. So in our paper, currently, we are focusing on the following setup, where we have two multi-morbidity conditions, Y1 and Y2, and a common risk factor X that affects those two conditions simultaneously. Okay, and then Y1 and Y2, they are genetically correlated, and their genetic correlation can be attributed to the genetics that are associated with the common risk factor. So this is the model, this is setting we are interested in our paper. And then again, for this common risk factor, it might have different some components that affect those pair of conditions in different ways. So this is where we can use cluster analysis to help understand the shared causal pathway of these condition pairs. So here's a hypothetical example to illustrate cluster analysis in the context of multi-morbidity. So suppose we have three sum components in our common exposure X from X1 to X3. So these sum components have different causal effects on those condition pairs. For the first subcomponent X1, it leads to increasing risk in Y1, but it would decreasing risk. It would lead to decreasing risk for the condition Y2. While for the subcomponent X3, it leads to increasing risk in Y2, but it has no effect, no causal effect on Y1. So the only component that leads to increasing risk for both conditions is Y2. So by doing cluster analysis, we can discover the set of SNPs that are associated with increasing risk for both conditions. So by doing cluster analysis, it can help us to understand the mechanism underlying the coexistence of both conditions. So this is why we can use, that's how we use cluster analysis to investigate the shared causal pathway of the condition pairs in multi-morbidity. Okay, so next I will show you how our method discover the SNP clusters. So when we observe, if we see, if there are if there are multiple slopes in the data, an important observation is that for SNPs that are surrounding the same slope, they would have similar ratio estimates to each other because they are surrounding the same value. So based on this observation, our strategy to discover SNP clusters is that we classify the SNPs as in the same cluster if their ratio estimates are similar to each other, or in other words, we classify the SNPs as in the same cluster if they actually estimate the same causal effect. Okay, so our method is based on the agglomerative hierarchical clustering algorithm, and all the inputs we need for our method are all the SNP ratio estimates and their standard errors. So all those estimates and also all those inputs can be estimated from the GWAS summary data. Okay, so next I'll use an example, a simple example to illustrate how our method works. So in this hypothetical example, we have 5 SNPs. So correspondingly, we have 5 ratio estimates, which are denoted, which are illustrated by, I'll need to move this. So those 5 ratio estimates, they are denoted by those 5 circles around above the line. And also in this example, we assume that from exposure to the outcome, we have 2 different causal effects, which are alpha 1 and alpha 2. Okay, so of course, in reality, so of course, in reality, we couldn't observe true causal effects, and we couldn't observe the color to mark the cluster membership. So all we can observe are just those 5 ratio estimates, right? But for illustration purpose, I will still show the color as a membership, and I will still show the true causal effects. Okay, so at the beginning of our method, we have 5 ratio estimates, and we view each one of the ratio estimates as an individual cluster. So at the beginning of our method, we can say that, okay, we have 5 clusters. So the thing we do next is that we calculate the weighted Euclidean distance between each 2 of the clusters. So weighted Euclidean distance is just to measure the similarity between each 2 of the clusters. Okay, so we measure the Euclid pairwise weighted Euclidean distance between each 2 of the clusters, and next we will merge the closest 2 in terms of the Euclidean distance. So we find out the closest 2 and we merge them into 1 cluster. So in this way, from 5 to 4, we will have 4 clusters left. So now again, among those 4 clusters, we calculate the pairwise Euclidean distance, and again, we merge the closest 2 clusters into 1 cluster. So now we have 3 clusters left. So this procedure just keep going and going. We measure the Euclidean distance and we merge the closest 2 into 1 cluster. So this procedure would stop until all those ratio estimates are merged into 1 big cluster. So for each step, we merge 2 of the clusters. So for each step, the number of clusters would decrease by 1. So when all the ratio estimates are merged into 1 big cluster, this will be the end of the first step of our method. Okay, so the point of this whole merging process is that for 1 ratio estimate, it will always merge with the ratio estimate that is centered around the same causal effect before it merges with ratio estimates that center around other causal estimates. So based on this, along this merging path, there must be, in theory, there must be 1 step where the ratio estimates from different true clusters are perfectly separated. So by the end of the first step, we will have a merging path looking like this, which keeps a record of how we merge this ratio estimates from 5 clusters to 1 big cluster. So we know that somewhere along this path, the true underlying clusters are somewhere along the path. So the next thing we want to do is that we want to recover those true underlying clusters from this path. Okay, so again, for illustration, I will still show the colors as the cluster membership. Okay, so the thing we do to recover those true underlying cluster is to use the Q-test. So we can apply the Q-test to a set of ratio estimates. So intuitively speaking, so the Q-test, it checks the degrees of heterogeneity of the set of the ratio estimates. If we do not get rejected by the Q-test, then we can say that, okay, those ratio estimates are highly similar, and we can classify them into 1 cluster. But on the other hand, if we get rejected by the Q-test, we might say that, okay, those ratio estimates are very different, and we shouldn't classify them into the same cluster. Okay, so we apply the Q-test from the top of the merging path, which is the biggest cluster that contains all the ratio estimates. So we apply the Q-test to the ratio estimates in this big cluster, and we ask, can these ratio estimates pass the similarity check? Can these ratio estimates pass the Q-test? So in this case, we would get a no, because all those ratio estimates, they are very different because they are surrounding different causal estimates. Causal effects. So we will get a no, we will get rejected by the Q-test. But after we get rejected, we will move to the next layer, this layer where we have 2 slim clusters. And again, we apply the Q-test to each one of these clusters, and we ask, can these ratio estimates within each cluster pass the Q-test? So in this case, we will get 2 yes, because the ratio estimates in this cluster are surrounded by the first causal effect, and the SNPs in the same cluster are surrounded by the second causal effect alpha 2. So in this way, by doing a Q-test in a downward manner along the merging path, we manage to recover the true underlying SNP clusters. And next, we just need to estimate the 2 causal estimates using the 2 SNP clusters that we discovered. Also, for the Q-test, we set the threshold p-value as 0.1 divided by log n, and this is just following some theoretical recommendation to control for the type 1 and type 2 errors of the Q-test. So this is how our method discovers SNP clusters. It can be applied for the settings for both 1 outcome and 1 exposure, and a setting with 2 outcomes and 1 exposure. Okay, so our method has some advantages and features over the existing method. So we have conducted simulation studies. So our method, it performed well in terms of discover the SNP clusters, and it is much faster than the existing method, MR-Clust. So this is the figure to show the running time of those 2 methods. So on the x-axis, we have the number of SNPs, and on the y-axis, we have the running times in seconds. So this red curve is the running time of our method, and this blue curve shows the running time of MR-Clust. So firstly, we can see that the running time for both methods would increase as the number of SNPs increases in the cluster analysis. But the MR-Clust, it would spend much more running time for our method. So if we use the same setting as in the running time test, and we carry out a cluster analysis across the phenome for 1,000 trees, and for each tree, the cluster analysis involved 200 SNPs, then the running time of our method would be around 12 minutes, but for MR-Clust, it can be as long as 10 hours. So our method is both reliable and fast, so it can be applied to a large number of multi-morbidity condition pairs to do cluster analysis. And also our method, it accounts for the uncertainty in the summary data estimates instead of treating them as fixed point. And also the method, it can handle the heterogeneity in the ratio estimates caused by pleiotropy. So we don't need to pre-specify how many clusters are there. The method, the algorithm can decide how many clusters are among the SNPs. And we also developed a 2-step variation of the method, so we can remove the outliers in the ratio estimates. And most importantly, we extend the method to the MR setting that I introduced previously, where we have 2 outcomes and a common exposure. So in this way, it can help us to further investigate the shared causal pathway between the condition pairs. Okay, so next I will show you some of the results when we apply our method to estimate the causal effect of body fat percentage on type 2 diabetes. So we use a 2-sample summary MR design where we have 487 SNPs, and the SNP exposure summary data are from this paper written by our colleagues in Exeter. In this paper, there are 36 of those SNPs are evidenced to be associated with favorable adiposity, where in other words, those 36 SNPs are associated with decreasing risk of type 2 diabetes. And 38 of those SNPs are evidenced to be associated with unfavorable adiposity and increasing risk of type 2 diabetes. But when we do cluster analysis using our method, we do not use any of those label information of favorable or unfavorable adiposity. We just treat all the SNPs as unlabeled, but afterwards, we will check if our cluster results are inconsistent with the findings in this paper. Okay, so this is a scatter plot for the 487 SNPs. It's about the SNP associations. So on the x-axis, we had the SNP exposure associations, and on the y-axis, we had the SNP outcome associations. So, and this figure shows the clustering results from our method, where we can see that the method identifies 3 clusters. The first cluster marked by blue, indicating increasing risk from body fat percentage to type 2 diabetes, and the other 2 clusters marked by red and green, indicating a negative effects, which is a decreasing risk from obesity to type 2 diabetes. There are a couple of dots here, point here, marked by blue. It is classified into the Jacques cluster. This means that, okay, those SNPs, they are not assigned to any of those clusters. Okay, we adjust our method using the 2-sample outlier remove procedure, and we can see that more of those outliers are assigned to the Jacques cluster, but still we identify 3 SNP clusters, 1 positive cluster and 2 negative clusters. So this result supports the conclusion that the metabolic effects from body fat percentage on type 2 diabetes are heterogeneous So some components of obesity would lead to increasing risk of the type 2 diabetes, like the one showing in the blue cluster, and some components of obesity, it would lead to decreasing risk of type 2 diabetes. Okay, and then we also check the cluster results of those pre-labeled favorable and unfavorable SNPs. So for those pre-labeled favorable and positive SNPs, which are supposed to be associated with the decreasing risk of type 2 diabetes, all of those SNPs are assigned to the cluster with negative estimates, meaning that they are associated with decreasing risk of type 2 diabetes. And for those pre-labeled unfavorable and positive SNPs, which are supposed to associated with the increasing risk of type 2 diabetes, 78 of those pre-labeled SNPs are assigned to this cluster with a positive estimate, which do indicate increasing risk of type 2 diabetes. So from these results, we can say that our conclusion is inconsistent with these findings, with the findings in this paper. So which can serve as a validation of the method. Which can serve as a validation of the performance of our method. Okay, and then we also apply our method to investigate the causal effects of body fat percentage on a pair of multi-morbidity conditions, type 2 diabetes and osteoarthritis. Okay, so here we use a 3-sample summary data MR design with 487 SNPs, which are the same as in the previous application. And here is a scatter plot of those SNPs. But one thing to notice is that in this scatter plot, it's not about SNP associations. It is about SNP ratio estimates. So in the x-axis, we have the ratio estimates for the first outcome, type 2 diabetes. And on the y-axis, we have the ratio estimates for the second outcome, osteoarthritis. So each of the points represent a specific SNP. Okay, so this figure shows the cluster results using our method. So we can see that we identify 5 clusters with different causal effects on the condition pairs. And again, we adjust our method using the 2-step outlier remove procedure. So after we remove the outliers and redo clustering, we identify 4 clusters that identify different causal effects from the common exposure to the pair of conditions. Okay, so we base our analysis with the outlier removed results with 4 clusters. Okay, so next we want to check the causal effects identified by each one of the clusters. So in this figure, in this panel above, we have the point estimates and the confidence intervals for the first on the causal effect for type 2 diabetes given by each one of the clusters. And on this panel below, we have the point estimates and the confidence intervals for the causal effect on osteoarthritis given by those 4 clusters. So we start with cluster 1 marked in red. So we can see that cluster 1 is indicating a positive causal effects for both conditions, which means that it indicating increasing risk for both conditions for SNPs in cluster 1. And then for SNPs in cluster 2 marked in blue, indicating increasing risk for type 2 diabetes, but no effect for osteoarthritis. And for class 3 in green, indicating decreasing risk for type 2 diabetes, but increasing risk for osteoarthritis. And for the last cluster, indicating decreasing risk indicating even larger negative effects for type 2 diabetes, which is a decreasing risk, but indicating no effects on osteoarthritis. So in this way, we discover different clusters. We discover different sets of SNPs that are indicating different pathways underlying the pair of type 2 diabetes and osteoarthritis. So based on this cluster analysis, we want to further investigate the information reflected by the SNP clusters. What we do is that we conduct an enrichment analysis using an R-function phenoscanner in the following way. So firstly, within each of the SNP cluster, we look up all the SNPs in the GWAS catalog for their correlated traits using the R function phenoscanner. And then we extract all the traits that are significantly correlated with at least one SNP in this given cluster. And then for these significant traits, we test the hypothesis of being correlated with this trait is independent of being in this given cluster using the one-site Fisher's exact test. So if we get rejected by this test, then we can say that, okay, SNPs in this given cluster are correlated with this trait more than SNPs in other clusters. Or in other words, we can say that this given cluster is enriched with SNPs that are associated with this trait. Okay, so for all the traits that pass the Fisher's exact, that get rejected by the Fisher's exact test, we classify them into three categories: the obesity-related traits, cardiovascular traits, and miscellaneous. Okay, so this table summarizes the enrichment analysis results. So, for example, for class 1, which indicating increasing risk for both conditions, increasing risk, it is enriched with 9 obesity-related traits and some traits that might reflect lower socioeconomic economic status, like more time spending watching TV and absence of qualifications. And for class 4, which identify a big negative effect for type 2 diabetes, but no effect for osteoarthritis, it is enriched with 4 obesity-related traits, and it is the only cluster which is enriched with cardiovascular traits, which are lower cholesterol medication and a lower risk of diabetes or mother. So from this enrichment analysis results, it might indicate that the pathway underlying the increasing risk for both conditions, it might not through a methodological pathway, and we might want to further investigate the roles of some of the traits, maybe using a multivariable MR studies. Okay, so for future works, in terms of methodology, we will extend our multi-morbidity model, especially to allow for direct causal effects between the condition pairs. And we can also explore different hierarchical clustering algorithms, like the Bayesian-based or density-based method, so we can produce more robust cluster methods. In terms of application, we will apply our method to more multi-morbidity condition pairs to investigate their shared causal pathway. And we will also explore different tools to further investigate the information reflected by the SNP clusters that we discovered beyond the phenoscanner. Okay, so this is the end of my talk. Thank you very much.
Thanks very much, Xiaoran. Really nice talk. A really good overview of what you've been doing, leaving many details out as well. So let's open the floor to questions. I can see that Vivian, is it? You have your hand up from IARC.
Yeah, thank you for this very interesting talk. I have a few questions, but so maybe I will start with a first easy one regarding the clustering. Which kind of linkage did you use, and how could it affect the results? Like, did you use a single linkage or complete linkage, word linkage, to compute the distance between the clusters?
Okay, so in the original agglomerative hierarchical clustering algorithm, they just use the Euclidean distance. So here,
But so to measure the distance between two clusters, do you measure the minimum distance between points within the clusters, or the maximum, or the average?
We measure the average. Yeah, we measure the average.
So the word distance. And did you try to look at different options just to check the robustness of the clustering and how it can affect?
Yeah, we conduct the simulation results, but using individual level data, and we found out that the cluster results using different of the linkage, it basically produce very similar results. So this is why we just use the average. Yeah.
Okay. If I may, just another question.
Mm-hmm.
so if I understood correctly, like, I mean, the general idea is that there might be two components within X, so X1 and X2.
Yeah.
So does it mean first that well, actually X is not really the exposure we would like to measure, but we would rather want to measure X1 or X2, and so X is just like a proxy for the two variables. So I can see that Jacques is saying yes, so I guess it's a yes.
Yeah, I was thinking that, for example, if we want to estimate the cause effect of obesity to the metabolic conditions, yeah, of course we can measure different subtypes of obesity that's correlated with fat distribution. But in sometimes maybe the data, they might not be available, and we can only use the single proxy for the exposure. So I guess in this way, the cluster analysis would be very useful.
Okay, and so if you have like alpha 1 and alpha 2, if you have like two clusters, how can you know whether, let's say, alpha 1 is the causal effect of two, I mean, there are the causal effect of two components, or like of one, I mean, causal effect derived from SNPs without pleiotropy, and causal effects?
That's a good question. So we say that we might observe multiple slopes in the data. It might be because of multiple causal mechanisms, right? But it might also caused by the unbalanced pleiotropy. So the direct statistical results from our method is that, okay, we can only produce different clusters that each identify the same causal estimates. But from those statistical results, we cannot tell, okay, this cluster is because of different components or different causal mechanism, and that cluster is due to pleiotropy. So this is why we need to do further analysis to investigate why we see different clusters. For example, okay, let's say we discover two clusters with alpha 1 and alpha 2, and then we do the enrichment analysis for G1 and G2, and we might see that, okay, G2, it is correlated with a large amount of traits that might not look very relevant for our exposure or outcome. Then we might suspect that, okay, the heterogeneity in the ratio estimate caused by G2, it might be because of pleiotropy instead of a multiple causal mechanism. Yeah, the direct answer is that we cannot tell directly
we discussed
if
this
the clusters are caused by mechanisms or pleiotropy. Yeah,
this specific point, don't we, that it's hard to disentangle the two things.
I'm
conscious of time. Well, let's ask one more question before we move on to the second talk. So Maxim, do you want to ask your question?
Yes, thanks very much. Very interesting talk. I'm very impressed. My question is about your way to remove outliers. From the graphs you presented, some SNPs are pretty obvious outliers, but some are less so. And when you remove them, I'm curious how you do that. Thank you.
Okay, so this is a two-step procedure. Okay, so in the first step, I'll just show this. So first step, okay, we just use our basic version of method that I introduced previously. So this is the results. Okay, so now we have 5 clusters, right? So within each cluster, we can calculate the individual contribution of each SNP to the heterogeneity of these clusters. So then after we get the individual contribution to the degree of heterogeneity of the clusters, we will set a threshold. If for a certain SNP, it contributed too much to the heterogeneity, then we will view it as outliers, and we will put it in the junk cluster.
But how do you set up the threshold? What's the criteria for this threshold? Is it arbitrary, or is it something more specific?
So the way we measure the heterogeneity within a cluster is using the Q statistic, and we can calculate the individual Q statistic using for each one of the SNPs.
Okay.
And this individual, individual Q.
Yeah, I think the reason why some SNPs that look like large outliers aren't removed, and some SNPs that don't look like such large outliers are, is that there's some information missing in the plots. Each point is actually should have a distribution around it in 2 dimensions. So there's uncertainty, and if the SNPs have different allele frequencies, those confidence regions will be much larger or much smaller.
Okay.
But we've just used we fixed a threshold, haven't we, for determining whether a SNP is an outlier or not.
Okay, thank you.
Yeah, but so there is some arbitrariness to it, but great. thanks everybody for all of the comments and questions. Please feel free to reach out to Xiaoran if you have anything more detail that you'd like her to answer. But let's move on to our second talk now. Ruth, would you like to introduce Jacques?
Yeah, definitely. Thanks everyone, and thanks for that, Xiaoran. That was really interesting. So I'm now going to introduce someone I know through our work in the National Cohort Studies, which is the network of population studies which was established during the pandemic. So we have Wels, I think, phoning in from Japan as well, which is really exciting. So the great thing about the NCS is it's brought together lots of different disciplines, and I've certainly learned a lot from working with Wels and people like him. Wels is a really engaging collaborator, so it's going to be really great to hear his work so far today. So his background is in quantitative sociology. I think his primary research interest is in the association between employment, work, social protection, and mental and physical health. But today he's going to be presenting his work on comorbidity and COVID-19. So we know obviously that comorbidity is a key variable in explaining severe forms of COVID-19 and mortality. But also there is potentially a key social impact of COVID-19 on the mental health of those suffering from multiple long-term conditions. And that's what Wels is going to present about today. I believe it's a work in progress, but really interested to see what you've got to share with us. Thanks, Wels.
Thank you very much. Thank you for having me on this meeting. I wouldn't say I'm very happy about it because it's always stressful to present online, and I think it's very bad for my future comorbidities as well. I'm very stressed to present online, so I'm sorry if I'm too fast, not clear enough, or if I look very stressed. I'm going to try to share my screen if it works. Yeah, I guess you can all see this, and even better that way, right? Wonderful. Well, first, as Ruth said, and Ruth, thank you for the invitation. I'm not a specialist in multimorbidities or comorbidities, basically. And when Ruth asked me whether I wanted to present this study, which is ongoing, which is not even finished, which is not even published, I thought what I committed to. I mean, this is a big mistake. First, presenting online from Japan at a time when I should eat. First mistake. Second mistake, we're all very tired of COVID-19 research, honestly. We want to move on. But I mean, I should advocate my own, this study as well, saying that the good thing, at least with COVID-19, is that it has kind of exacerbated what we would have observed in the real world. So it's a good kind of natural experiment. I take it with a pinch of salt, but I think it's pretty interesting. Another point why I didn't want to present the study, and I a bit regret, is that time was really short, and what I'm going to show you, as I said, are only very preliminary findings, and I should add to end this very long apologizing introduction that I'm not an expert in comorbidity. I told you I'm an expert in employment and mental health and physical health. So if you do any research on employment, feel free to contact me. I might be better at that. Okay, so as we say, there's some evidence on the association between multimorbidity or comorbidity and mental health during the pandemic, but it's limited to only a few amount of studies. And it was only at the early stage of the pandemic. No study has covered a long time over the pandemic. Why? Well, as Ruth said as well, she did my introduction much better than I will do. People with multi or comorbidities were more at risk of COVID-19 infection first. The second point is also a lack of access to community health, social care services, and support from other health professionals. Flowing from that, we have developed 4 research questions that we wanted to look at. The first one was to look at whether the presence of more than one chronic health condition, which you call comorbidity, was associated potentially with poor mental health and well-being outcomes during the pandemic. Second research question was to look at whether some health conditions, some specific health conditions, were more likely to be associated with poor mental health and well-being outcomes during the pandemic. Third research question, well, as you all know, and I'm going to develop that a bit later, but there's a shielding statue that was developed at the early stage of the pandemic, and some people received a letter from the NHS asking them to shield. And well, we discovered in the data that some people declared receiving the letter from the NHS, but didn't report any health condition, which was of interest. So we did an interaction between health condition and shielding statue to see whether we had actually an interaction that could be of interest. And finally, the fourth research question is to look at some socio-demographic effects that we might observe. And here I'm going to speak specifically about the self-reported financial difficulties that could explain differences in the association on research question 1 on the association between comorbidity and mental health. So as Ruth said as well, again, a wonderful introduction. This is part of the COVID-19 longitudinal health and well-being core study. Basically, you might have heard about it, but these are a group, a big group, if I may say, where we use data sets from different institutions. So these are more or less all the data set, but there might be some more, and all the different institutions involved in this project. For this specific, well, I should also make some publicity, which I'm very bad about, but we published a lot of papers, including a few about employment, which I'm very proud about. So one was about the furlough scheme, and one that is preprinted, that has been preprinted recently, is about home working. As I said, for this specific study, we only focus on 8 data set. When I say data set, I mean longitudinal studies or cohort data set. So their main feature is that they track people over time and over different time points throughout the pandemic, but also before the pandemic. We focused here only on 8 specific data sets because those data sets got enough information for what we were aiming to look at. It was impossible with some other data set that didn't include relevant information. What we did is that we homogenized, I cannot pronounce this word, but I need to use it quite often, so I apologize in advance. But we homogenized variables across the different studies, which I mean, the result of that is that it reduces the complexity also of the studies. So that's one of the pitfalls of using that kind of method where we use different studies together. We conducted separated analysis on each data set, and then we meta-analyzed the estimates. I should say we will meta-analyze the estimates, because here I'm going only to show you results for 5 studies. The other coefficients are not reported for BCS, Generation Scotland, and ALSPAC, and I apologize about that. So the title was misleading. Here we focus only on 5 studies. As I said, all the studies collected information over different time points throughout the pandemic, 3 waves, except for ELSA, that has only 2 waves, wave 1 and wave 3. But we also have pre-pandemic information. For the study, so I repeat that each study is made separately on each data set. We have 4 outcomes of interest that we have coded on a binary basis: life satisfaction, high life satisfaction versus low life satisfaction, self-reported health, good versus poor, psychological distress, low versus high, and social isolation, low versus high. So 0 good, 1 bad, if you want to remember how to interpret the coefficients. Of course, the standardization of those variables was a bit complex because questions were not exactly asked the same way and modalities were not exactly the same across studies. I'm not going into details about that, but we have homogenized that as we did in the previous studies that I mentioned just previously. Our exposure is, where we have 3 exposure. The first one is to look at the health condition as such, and that was quite tricky, and Ruth remembered that, because we had to find morbidities or health conditions that were the same and phrased the same across the different studies. So we picked up only, if I may say, 6 modalities, which are cancer, diabetes, high blood pressure, chronic heart disease, respiratory disorder, and obesity. For most studies, we picked up a result of BMI more than 40, which is high obesity, again, if I may say, to avoid including people that are just above the range. And this echoes what has been done in previous studies as well, so we didn't create that. And what I show you on the table, very small here, it's very small because I don't want to look at it. No, that is not true. It's very small because I want to show you the complexity of all these measurements across studies. So basically, health conditions were measured for each study at the start of the pandemic, at the early start. So we couldn't assume a reverse causation, if I may say, that the pandemic would have caused this health condition. No, they pre-existed. They were there at the beginning of the pandemic. Then that's the one that is of interest for this paper. We calculated the variable of comorbidity, which is more than one health condition. Of course, here it's a limited definition of what comorbidity is because it's more than one of the 6 health condition that we have picked up because they are common across the studies, but thanks, if I may say, they are common across the population as well. And the third exposure is, as I said in the introduction, the interaction between comorbidity and shielding statue. As I've said previously, I hope you remember, people will receive a letter from the NHS asking them to shield, and we did an interaction between those 2 variables. So these are our 3 exposures, and we control for a set of I don't like the term covariates, so I should say we control for control variables, and we have 2 levels of adjustment: a basic adjustment where we only control for pre-pandemic COVID health, whole health measurements that were available in pre-pandemic sweeps. We also control for sex or gender. It was not phrased the same way across the studies. So sex or gender, depending on the studies. And we have a full adjustment that additively controlled, so we include pre-pandemic health and sex and gender for country or county, depending on how you want to call it, England, Northern Ireland, Scotland, Wales. Highest level of education. Here we only distinguish degree and no degree for reasons that you can understand due to the homogenization across the data set. Self-reported financial well-being, comfortable or wide difficult, and the employment statute, whether people were working or not working. When I say working, this includes self-employed and furlough, so those who are associated to any form of employment versus those who are not. I should say something very important that is not in my slide, that we focus on the population that is more than 50, which I think is of interest to say. So I should mention that and be clear about this. The model where we use a random effect, mixed effect, this is the same in longitudinal data set over the 3 time points that I mentioned, but controlling for pre-pandemic health with a modified Poisson regression for binary outcome. Mixed random effect accounts for the change over time point, and the modified Poisson regression calculates for the relative risk ratio, which, as you know, are better than the usual odds ratios. We have, as I've said, 2 adjustment level, 3 stratification level, but here I will only focus on perceived financial hardship, and we have a weighting. So we weight for population weight when available in the data set, and we multiply this population weight by an inverse probability weight calculated based on pre-pandemic response information to be sure that we don't drop people we shouldn't drop because we select pre-pandemic waves. Okay, I speak too fast and I'm very too stressed on this presentation. So am I clear so far? Do you have any question about the methods? Because I feel I've been pretty fast. So please ask me your question, then I can breathe.
You're doing great. Please
That's not a question.
Sorry, can I just,
yes.
can I just ask a quick question? Hi, it's Peter Horton. So why are you using a Poisson regression for binary outcomes instead of a logistic regression? This is probably a dumb question, but...
No, that's a very good question on which I cannot answer properly without being prepared. But the problem, and Ruth knows that, so maybe you can help me to answer. But the problem is that when you calculate aware, an odds ratio, basically the size of the population is going to have an impact on the coefficients. So basically you will, overestimate the impact or the effect of an association if you use an odd ratio. Whilst if you use a modified Poisson regression, you wouldn't overestimate the relationship due to population size. Ruth, I'm right? I'm correct. Okay. So basically that's the main idea. If I want to be very honest with you, if you compare odds ratio with relative risk ratio, most of the time they go in the same direction. So it doesn't change much, except that the relative ratio usually do not exacerbate the relationship that you observe. So it's more accurate, and it allows you to calculate for risk, a relative risk ratio, instead of an odd ratio that usually people understand a little bit more. Although I'm not sure about that, but odds ratio are a bit complex to understand for common people, and even for myself. When I see an odd ratio, I don't know why a relative risk ratio seems more intuitive, if I may say. So those are the two reasons. But the first one is a more robust reason to use modified Poisson regression. I hope I've been clear enough.
Yeah.
Thank you. And finally, as I've said, we estimate. We meta-analyze the estimate using a random effect. And what we need to look at when we do that is looking at the meta-analyzed estimate, but also at the heterogeneity across studies, which is of interest. I'm moving fast to the result. So to be very transparent with you, these were produced yesterday night. So it's very fresh, and we're going to try to interpret them together. But this is basically the result when we're looking at comorbidity, the association between comorbidity and life satisfaction. You can see the estimate for each study separately, as well as the 95% confidence interval, but also the meta-analyzed estimate with a confidence interval. And what is of interest here is that we observe a positive association, and even significant for twins UK, between comorbidity and life satisfaction, but not in NCDS. Which is one of the cohort study. And well, I thought it was due to a problem in coding. Maybe life satisfaction was not coded the good way, but it's not. I've checked several times. So it's very interesting, and Ruth, you might agree with me, and some other people too, is that when we replicate exactly the same analysis with the same variable and with the same hypothesis on different study, sometimes we have huge heterogeneity across the estimates, which advocates for doing more kind of research where you compare different cohorts and different studies together, and then produce meta-analyzed estimate, or at least look at the heterogeneity. Because imagine if I used only NCDS, what I will say comorbidity is good for life satisfaction. If you have comorbidity, well, you're more likely to have a better life satisfaction than those who have none, which doesn't sound very, very intuitive. Yeah, so this is for life satisfaction. I can move to another one that is significant for all studies and goes in the same direction. It's a huge association between comorbidity and self-reported health. Here you can see on the left we have the basic adjustment, and on the right the full adjustment, but you can see that in both we have 1.35, 1.34 relative risk ratio of an association between self-reported and comorbidity. It goes more or less the same for psychological distress, but not significant. And it goes on the same way for social isolation, but again, not very significant. To sum up, we observe an association that when we look at the change over time during the 3 time points through the pandemic between comorbidity and social isolation and the other variables, but the association is strongly significant only when we're looking at self-reported health. I try to be a bit fast. Here I looked at the association between these different outcome and health conditions. I didn't meta-analyze the results, so these are the results by study. What you can see to me, and trust me because it's very small and I try to be very fast, but what you can see is basically we have a positive association for all health conditions taken separately, except for obesity and to a certain extent, except for diabetes. This is very gross. This is not very detailed, so please take it carefully as well, but I wanted to show that to say that, well, there are differences across the different health conditions as well. We also looked, as I've said, at the interaction between life satisfaction, the interaction between shielding stature and comorbidity, which we thought was of interest because, as I've said, there's a significant number of people who received the letter for shielding, but didn't report any of the 6 health conditions that we mentioned. Some people also receive a shielding letter and reported those conditions. And some people reported conditions, but didn't receive a shielding letter. So that's of interest to look at whether we have a significant association. And this is not the case, except when we're looking at self-reported health. Basically, when we're looking at the interaction term between shielding and health condition, we have a significant negative relative risk ratio. So if I give you the example of NSHD, for example, we have we're going to obtain for the full model a relative risk ratio of 0.4 for dose shielding. This is for the main effect. Main effect for comorbidity, that is 0.20. And when we're looking at the interaction between shielding and comorbidity, well, then we have minus 0.14, which makes a total, if we add up the main effect and the interaction term, of 0.10. So there's a kind of, how to say, slight impact of shielding stature, very strong impact of comorbidity, and medium impact of shielding and comorbidity together, which in a way confirms that it makes more sense to look at comorbidity than at shielding because of this reporting problem. And also, if you take the shielding stature, if you had a cancer 7 years ago and you've been cured and you're absolutely fine, you were still likely to receive this shielding letter, for instance, which also explains that we have people who were requested to shield, but actually they didn't have any condition for which they should have shielded. Is it a good conjugation? But yes. Okay. Nothing significant for psychological distress, nothing very significant for social isolation, neither. And I conclude in 2 minutes by looking at the differences by financial well-being. Here we have created 3 categories of financial well-being: comfortable, all right, difficult, and we just replicate the analysis for research question 1, but by financial well-being. And this is pretty tricky to look at, and it is, how to say, first, there's heterogeneity again, which makes it very complicated, particularly for those reporting having a difficult financial situation. Huge heterogeneity, but that also explained by very small samples. All cohorts, the CLS cohorts, so NCDS, for example, BCS and NSHD tend to be middle class or upper middle class more, which is a bit complicated. So it reduces the amount of people we have and might produce that kind of estimate. So that's a bias, but we see no very clear trend on the relationship between life satisfaction and comorbidity by financial well-being. It's a little bit clearer and a bit stronger, actually, when looking again at self-reported health. Here we have an association. This association is not significant at 95%. I will bet, though, that this association is significant at 90%. But again, it's not different from one subgroup to another, which is very complicated. So this confirms what we observed previously when we put everybody together. But when we distinguish here by financial well-being, we do not obtain, and I was very surprised about that, any significant difference. Still 1 minute and I'm done. Same result for social isolation as well. And I'm moving to my conclusion, if you don't mind. So research question 1, presence of comorbidity associated with poor mental health. Yes, but it's only significant for self-reported health. Research question 2, some health conditions more likely to be associated with poor mental health. Yes, they are, except obesity, although obesity is associated, I didn't say that previously, with social isolation, and also for diabetes. Research question number 3, is there an interaction between the presence of one or several health condition and having been requested to shield? No. Significant interaction except for self-reported health. And finally, that's just what I've said. No. Is there a significant effect of financial well-being? We didn't find so far significant association, but there might be some potential biases in the way we've been coded this financial well-being variable that we need to look at. So these are the findings we did so far. That's the work I did last night. I apologize if I was stressed fast and not clear enough, but hopefully in 2 months, you will see a wonderful preprint where everything will be clearer. So fingers crossed for that. And thank you for your attention, and be kind with your comments, please. I know you are, but.
Thanks very much. Yeah, especially for sharing work in progress that will, in a couple of months, be much more polished. But yeah,
hopefully.
Do we have some questions? Maybe I could just ask a quick question. So do you think that shielding on balance was good for people's health or bad for people's health? I mean, did it make their lives less stressful, or did it lead to negative effects of isolation?
Yeah, no, that's a good question. And to be honest, we didn't look at that question because the purpose of our interaction effect was in a way to exclude the fact that shielding was relevant in looking at the association between comorbidity and mental health. And in a way, it was not. Also, there's a difference between receiving the letter to shield and shielding behaviors. And there's a huge difference. A lot of people received the letter but didn't shield. There is one paper written on that with ELSA data by Giorgio Di Cesa, I think, where they look at this gap between shielding statute and shielding behavior and huge differences. But of course, the shielding statute is not going to have an impact or an association with your mental health. It's more the behavior you're going to have due to this late shielding statute. So that's not what we looked at here. And what we wanted to show is also shielding is not so much of interest. What is of interest is health conditions, independently on whether people receive this shielding letter or not.
Great, thank you. Are there any other questions?
That I was very stressed. Ask me questions. No, at least I didn't stress for nothing. No. Oh no. Sorry. Thank you.
Please go ahead.
Okay, I'll ask a couple of questions. So one's just a point of clarification. So some of the analyses you showed looked at association with what you called health, and they seem to go, well, I thought the opposite way from what I was expecting. Is that because it was with poor health, like health issues?
Well, we're looking at several indicators of mental health, but they go
yeah,
on
so
the
not like, I'll come back to the life satisfaction one, but you had other ones where you talk, yeah, like self-reported health. So does that mean is a positive thing saying that you are more healthy, or is it saying that you have
no. Yeah, sorry, I've been a bit fast in explaining that in the introduction. You're right. So here we've coded it on a binary basis. So basically, self-reported health is a variable about general health. How do you feel in general? That's usually how the question is phrased, with something like 5 modalities going, and you know that going from good to bad or bad to good. And we've coded it as binary, with 0 being good and 1 being bad. So right. Basically, it goes on. Yes.
Yeah, so then these results make more intuitive sense to me, because otherwise it would seem the opposite way around from what I would expect. But then
it will be very strange.
But the same question is there with respect to life satisfaction. So again, how is that coded?
Exactly the same. So basically, good life satisfaction is, if I may say, is 0, and bad, poor life satisfaction is 1. And here it makes sense, except for NCDS.
Right. Yeah. Okay, so it mostly makes sense. Okay. Yeah. As I say, I was getting confused between whether it was poor life satisfaction or high life satisfaction. Thanks.
No, but it's my fault. I'm sorry. Maybe I should have put that on the title. On the title, we do that for the paper. But again, I'm puzzled by this NCDS results. So that's something to look at, and something we still need to do, I think, in general, is to look at the heterogeneity across the different studies, which I think is of interest, because we have a lot of way to explain what we are looking at, but little way, statistically speaking, to look concretely at what explains those heterogeneities across studies. But thank you for the question. I'm sorry, I should have clarified that a bit more. Thank you.
Thanks, Heather. Are there any more questions for the speakers? No? Okay. If not, then I want to thank both the speakers for really excellent talks, and for the audience as well for coming and providing such great feedback. I don't know if we've got a date in the diary next for our next meeting, Ruth. It's likely to be in a couple of months, is it? In April, maybe?
April, end of April, I think.
End of April. Yeah. So as always, please send speaker suggestions to myself and Ruth, and we'll do our best to try and invite them. So have a good week, everybody, and look forward to seeing you soon somewhere.
Thanks, everyone.
Bye-bye.
Thank you.
Bye. Bye.
Bye.